Hello and welcome back to Machine Learning. I'm Javita Christie, and in this video, we are going to talk about some problems in regression analysis and also the solutions to these problems. So let's begin. Before we begin, we are going to go through some assumptions that are made while performing a simple linear regression or even a multiple linear regression. Okay, so based on these assumptions, we will define the problems later on, and we will give some methods that can be used to solve those problems. So let's go through these assumptions first. So first, we have that the dependent variable y can be calculated or predicted as a linear function of a specific set of independent variables, okay, plus an error term. So this is nothing but, it is just describing the linear regression equation, right? That you have one dependent variable y, which you want to predict, and you have several independent variables x, which you want to use to predict y. Okay, if it's a simple linear regression, you will be having only one independent variable x. But if it's a multiple regression, then you will multiple linear regression, then you will be having several values of x and you will use those to predict y. Okay, and there's also an error term epsilon, okay, which is added to this equation because the equation is not perfect. It is always going to have some errors. The number of observations n, okay, the second assumption is that the number of observations n is greater than the number of parameters k to be estimated. So that means n has to be greater than k. All right, you cannot have, if you have 4 parameters to be estimated and the number of observations are less than that, it's not going to work. In any kind of machine learning algorithm, the more the number of observations you have, the better your algorithm will do. So having a large number of observations is very essential. The third assumption is that relationships determined by regression are only relationships of association based on the data set and not necessarily of cause and effect of the defined class. Okay. So relationships are completely dependent on the data set that you have provided for your regression. They do not show anything about the cause and effect of the defined class where they belong to. The next assumption is that the regression line can be valid only over a limited range of data. Okay. If the line is extended outside that range of extrapolation, then it may only lead to wrong predictions. So, for example, you are trying to predict some height and weight related thing that some height is given and you can tell the weight. So like you could make predictions within a given range. Okay. You couldn't just go beyond and give a height of like 170 centimeters and there is some person who weighs maybe 300 kgs or 200 kgs. That's an outlier which is not present in your data. And finding such a thing is unreasonable with a regression line that you have created using data where there is no such combination given, right? It's just nothing like that. It does not have any range like this. It does not have a weight of 200 kg anywhere, and you are using that now for prediction. So you're bound to get a wrong one. The next thing is that if the business conditions change, okay, and the business assumptions underlying the regression model are no longer valid, then the past data set will no longer be able to predict future trends. Okay, so whatever business rules or business trends you used while creating your model, if those conditions are changing, then the data that you have used to create your line is no longer valid, which means you can no longer predict the future trends using that past data. And finally, the variance is same for all values of x. So if you calculate the variance, we know the formula. We've seen that so many times before in the previous videos. So calculating the variance, okay, which is the square of the standard deviation. That is the same for all values of x. which is known as homoscedasticity. Okay, so we are going to see this later. We will see that later and you'll understand it better then. And the next thing we have is the error term epsilon is normally distributed, which also means that the mean of this error has an expected value of 0. So if you take the mean of these errors, it's going to be 0 because it is normally distributed. Okay, normally distributed, which means it has a normal distribution with a bell curve if you plot it on a graph. The next assumption is that the values of the error epsilon are independent and are not related to any of the values of x. What does that mean? It means that there is no relationship between some value of x and some value of y, okay, that are related to another specific value of x and y. So one pair or combination of x and y is not related to another pair or combination of x and y. That's the other assumption we are making. And other than these, we also have some problems with our linear regression model. So these are all the assumptions that we are basing all these problems and solutions on. So what are the problems? The first problem is multicollinearity, where two variables are perfectly collinear. Okay, what is that? First of all, multicollinearity. Two variables are perfectly collinear if there is an exact linear relationship between them. So we are supposed to have a linear relationship between x and y, right? That is what we want. But if there are lots of x values, do we want collinearity between them as well? Okay, but so multicollinearity is a situation in which the degree of correlation is not only between the dependent variable and the independent variable, but also there is some strong correlation within the independent variables themselves. So what is desirable is that there be a correlation between the independent variables and the dependent variables. But what is undesirable is that there is a correlation between the independent variables themselves. So that means one independent variable is affecting the value of another independent variable, and we don't want that in our model, because then your regression line is not going to be perfect, okay? Because the variables among themselves are linked with each other. So value of one affects the value of another. And this we want only with independent variables and dependent variable. We don't want this among the independent variables. The next problem is heteroscedasticity. Okay, so what is that? It refers to the changing variance of the error term. If the variance of the error term is not constant across the data sets, then you will have erroneous predictions. So you have to have constant variance of all the error terms that you have. So in general, for a regression equation to make accurate predictions, the error term should be independent, identically distributed. So these are commonly known as IIDs. And we saw this earlier as well when we studied central limit theorem. IIDs are independently, identically distributed variables. So what does that mean? They are independent, okay, which means all the variables are, all the x variables are not dependent on each other, and they have to be identically distributed. And in this case, this identical distribution is the normal distribution, okay? So identically distributed means all the variables should be following the same kind of probability distribution, which in our case is the normal distribution. Now, since we have seen all these assumptions and the problems which we have with linear regression, which we can face, we are going to see now how you can improve the accuracy of our model, which means how you can overcome some of these problems. So if you have high bias, okay, that means you have high values of epsilon, then your accuracy is going to be low because it is not close to the real value. If you have a high variance, then also your prediction is going to be low because your values are scattered about on the graph and they are not very close to each other. So it will make it difficult for you to create a regression line. If you have a low bias, then you will have high accuracy because your value will be close to the real value, the predicted value. And if you have low variance, then you can have high prediction. So these are some of the concepts that you need to know beforehand, um, before we start talking about accuracy and improvising it. Okay, so remember, if there is high bias and high variance, you will have less prediction, less accuracy. If you have low bias and low variance, then you will have better prediction and better accuracy. Okay. Now, how can you calculate or find out the accuracy? How can you improve the accuracy of a linear regression model? So there are three methods for that. The first method is the shrinkage approach. The second method is called subset selection. And the third one is dimensionality or variable reduction. So let's take a look at all these one by one. The first method we have is the shrinkage, or it's also sometimes called regularization approach. Okay. Few variables used in the multiple linear regression model are in fact not associated with the overall response, and they are called irrelevant variables. This may lead to unnecessary complexity in the regression model. Okay, so sometimes you are taking a data set that has, say, 10 columns, and you are not really trying to find out if those 10 columns help you to predict the 11th column or not. But you just apply linear regression just like that, multiple linear regression, and use all the columns and try to predict the 11th column. And some of those columns might not actually be helpful. They might be irrelevant while trying to predict the 11th column. So you're not considering that. Okay. And you have to do something about such columns. You don't have to take all the columns because they will unnecessarily increase the complexity of your model. So to reduce such columns, to remove such columns which are not useful, you have to perform a fitting, okay, where you involve all the predictors. And that this is the shrinkage approach. So in the shrinkage approach, you have to fit the model and involve all the predictors. However, the estimated coefficients are shrunken down towards zero relative to the least squares estimates. So what happens here is, with each value of x, you will assign a coefficient, and you will increase or decrease the value of the coefficient in order to specify how important those coefficients, how important those variables are. So for example, your equation will be y is equal to a1x plus a2x plus a3x and so on, and then the y-intercept. So all these coefficients that you have with different x1, x2, x3 values will have different weightage. So every column has different weight, and the columns that are not helpful to you while predicting the value of y will have nearly zero coefficient, which means their impact will be very less. So this is known as the shrinkage approach because it can reduce the overall variance of your data. And some of the coefficients might also become exactly zero. That means they have no role in predicting the value of y. The two best known techniques for executing the shrinkage approach, okay, are ridge regression and lasso regression. Lasso stands for least absolute shrinkage selector operator. So these are the two methods that can be used to implement to implement the shrinkage approach. So what is ridge regression? It performs a regularization, which is known as L2 regularization, in which it adds penalty equivalent to square of the magnitude of coefficients. Okay, so whatever coefficients you have, take a square of that, and whatever is the penalty related to that, you add that into your regression. And the lasso regression performs a regularization known as L1 regularization, which means it adds penalty equivalent to the absolute value of the magnitude of coefficients. It's not taking the square, it's taking the absolute value. So if there is a negative value, it turns into a positive value. Okay, so these are the two ways in which you can implement the shrinkage approach. to reduce the variables which are irrelevant to your prediction. The next method we have is the subset selection. Okay, so the subset selection method is used once again to improve the accuracy. And what do you do there? You identify a subset of the predictors that is assumed to be related to the response, and then fit a model using OLS on the selected reduced subset of variables. So in subset selection, we are using a completely different approach than in shrinkage approach. In shrinkage, what we did is we tried to fit the model using all the columns, and then we decided which of those columns is important and which is not important by adjusting the weights, okay, adjusting the bias. But in subset selection, we don't just fit the model on all the variables. We will try to take a subset of those variables from the beginning, okay, the subset of the variables that are very influential when you're predicting the value of y. So only such variables will be taken, and the model will be fit using OLS only on those variables. And there are two methods in which you can select these subsets. The first, you have the best subset selection, which considers the all possible subsets. So if you have k parameters, you will consider all 2k possibilities and see which one is the best. The next you have is stepwise subset selection, which has two options. One is forward stepwise selection, where you go from 0 to k, and also a backward stepwise selection, where you go from k to 0. So what happens in best subset selection? You fit a separate least squares regression for each possible subset of k predictors. So if you have k columns in your data set, you are going to take k subsets. Okay, you're going to take 2k subsets, which means you will take all possible subsets. You will try, combinations of 3 columns, 4 columns, 5 columns, everything, and try to create a least squares regression line for each of those subsets. And then what happens? You can pick whichever one is working the best. But for computational reasons, of course, you cannot do this. It's not very efficient if you have really large values of predictors. So this procedure, like I said, it considers all the 2k models. It will try to create a regression line for all the 2k models that you have and for all sets of predictors. The other one we saw was forward stepwise selection. What happens in that? It is a computationally efficient alternative to the best subset selection that we saw earlier. And in this, what happens? You consider a much smaller set of models, and that too you do it step by step, instead of taking all the models and then creating a line and then checking which one is the best. So here it begins with a model containing no predictors, and then the predictors are added one by one until all k predictors are included in the model. So you begin with 0 predictors, and then one by one go on adding the predictors, okay, till you have your enough number of k predictors to make predictions. And in particular, at each step, the variable x that gives the highest additional improvement to the fit is added. So at every step, you will pick a parameter that gives you the highest improvement, highest accuracy. It increases the highest accuracy while making predictions. That is your forward stepwise selection. We also have a backward stepwise selection, where it begins with the least squares model, and it begins with all the predictors initially. And then it iteratively removes these predictors one by one in every iteration, by picking the least useful predictor one by one. So that is your backward selection. The last method to improve the accuracy is known as dimensionality reduction, which is sometimes also called variable reduction. So the earlier methods which we saw, which were subset selection and shrinkage, control variance, either by using a subset of the original variables or by shrinking their coefficients to 0, right? So shrinkage approach was reducing the weight associated with that variable in order to diminish its importance. And in the other approach we saw, subset selection, what happened was we reduced the number of variables, parameters that we were using one by one. Okay. In dimensionality reduction, the predictors X are transformed and the model is set up using the transformed variables after the dimensionality reduction. So you're not talking about reducing the variables, but you're talking about transforming those X variables. So what happens here is the number of variables is reduced using the dimensionality reduction method. And to do this type of a reduction, there is an algorithm called principal component analysis, one of the most commonly used techniques for dimensionality reduction. We will be studying it later in one of the future videos. Okay, so it's called PCA, principal component analysis, which is used for dimensionality reduction.